All right, so what I want to do now is work through a few IR problems, okay? So what we're going to do is work on 3 problems here where we're going to try to solve the structure of an organic molecule when we're given the formula and the IR spectrum, all right? And in some of these examples, there will be, there's multiple structures that would be valid and correct, right? So we're just going to see if we can come up with a structure that makes sense, all right? So we're really given 2 pieces of information. We have our formula and then we have our IR spectrum. So it's important that when we have our formula that we use it, right? So what we're going to do here is calculate our DUs or DBEs first, right? Because that can give us an idea on how many bonds, how many pi bonds or how many rings that we have. So remember the formula for this is the number of carbons in the formula plus 1 minus the number of hydrogens plus halogens divided by 2 plus the number of nitrogens divided by 2. So if we plug this formula in, we have 6 carbons plus 1 minus 12 hydrogens over 2, right? And we always can ignore the oxygen. So this gives us a number of 7 minus 6. So here we have 1 DU or DBE. So that tells us that this is either going to have 1 pi bond or 1 ring. 1 pi bond or 1 ring. So that's going to help us solve this structure. All right. So let's analyze our IR. We go into zone 1. We've got a big broad peak here in zone 1. Okay, what does that represent? This is clearly going to represent an OH bond, right? And it can't be an NH, there's no N in our formula, so that's an OH bond. Zone 2, we draw our 3000 line. We have a few peaks between 3000 and 2850. That corresponds to sp3c to H bonds. Really nothing in zone 3. Next, in zone 4, we have a nice large peak in zone 4. That's clearly a carbonyl, right? And then as we get below 1450, we can basically ignore the rest of this, all right? So that's all we have, but this is important, right? We know that we have alkyl groups. We know that we have to have an alcohol, right? And because there's only 2 oxygens here, we know that then this needs to be a ketone. So what are some possible structures that can fit here, right? Again, we have 1 pi bond or 1 ring. We know what our pi bond is. That's the carbonyl, right? 6 carbons. So I can just draw 1, 2, 3, 4, 5, 6 carbons. We could put a ketone here and an alcohol there. That's a great structure that fits, okay? What else could we do? We could have a ketone here, 1, 2, 3, 4, 5, 6, and an OH there, right? We could have a ketone. There could be some branching here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Again, that would be another structure. We could have something like this. 1, 2, 3, 4, 5, 6. So there's a lot of different structures that would be acceptable that would have an IR spectrum that matches. Let's talk about a few structures that are not okay, all right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This structure would not fit, right? So if I just had my carbonyl at the end, right? This is the same molecule. That would not work. Why? This is an aldehyde peak, and what we should see is we do not have a peak at 2700, right? There's no peak at 2700. So this cannot be an aldehyde. These structures would not fit, right? Another structure that would not fit would be this, 1, 2, 3, 4, 5, 6. What's wrong with this structure, right? What functional group is this? That is a carboxylic acid. And what do we remember about carboxylic acids? This OH has to be an alcohol. It can't be a carboxylic acid because carboxylic acids come in zone 2. This is clearly the OH of an alcohol, right? So again, here's another structure that wouldn't fit. And of course, your structure obviously has to have 2 oxygens. It has to have 6 carbons, right? So if you drew anything with 3 oxygens or 5 carbons or 7 carbons, those wouldn't work as well. All right, so you can see here there's a lot of different structures you can draw. The key functional group you have to have is a ketone and an alcohol and having 6 carbons. So a lot of these structures here fit that. All right, so that's our first problem. Let's look at our second problem here. Okay, again, we're trying to figure out a possible structure here. First thing we want to do is calculate DUs or DBEs, right? How many pi bonds and rings we have. So remember our formula, the number of carbons plus 1 minus the number of hydrogens and halogens divided by 2 plus the number of nitrogens we have divided by 2, right? So this would be 9 minus 3/2 plus 0.5, right? So that would be 9 minus 3, right? So that's going to be equal to 6, all right? So here we have some combination of 6 pi bonds plus rings, all right? And a good hint for you is anytime you have anything that's greater than or equal to 4, that's most likely going to be a benzene ring, right? A benzene ring is 1 ring and 3 pi bonds. That would get you 4 DBEs, okay? So we're probably most likely going to have a benzene ring, plus we're going to need 2 more, right? 2 more rings or 2 more pi bonds, all right? So I'm just kind of putting this out here on the side to help us figure out a good structure. Next, let's analyze our IR. Zone 1, nothing substantial here, right? I draw my 3000 line. I have some peaks between 3100 and 3000. Those correspond to sp2c to h's. I have a couple of peaks between 3000 and 2850. Those are sp3c to h's. I've got a big sharp peak here in zone 3 that's at about 2200. So we know that this can be a carbon-carbon triple bond or a carbon triple bond to an N. What's going to make sense here? We have to have a nitrogen. So if you go back to zone 1, we have no NH2s. So that means this is most likely going to be my C triple bond N. I get to zone 4. I have a little bit of 3 or 4 small peaks here. Those are my aromatic overtones. So we've now really confirmed, right? We've confirmed that we have our benzene ring here. And just to finish that off, we have a couple of peaks at about 1600 and 1500, right? These are our carbon-carbon double bonds. And we can basically ignore everything below 1500 or so, all right? So if we look at our functional groups we've got an aromatic compound. We have a C triple bond N. I have to have some sp3 carbon. So let's figure out a structure that will fit here. So I can draw a benzene ring, right? I need to have 8 carbons, okay? So 1 carbon could be a carbon triple bond, the other one could be a methyl. So this is a structure that fits well. When you calculate your DBEs and follow that, you don't have to worry about the hydrogens, they'll match, right? This had 7 hydrogens. We have 1, 2, 3, 4, 5, 6, 7. So that fits. So this is a structure that works. At a basic level, I can't really tell if the methyl group is going to be ortho, para, or meta, right? So we could draw a structure where that methyl group is ortho. That would be a good structure, we could draw another functional group where that methyl group was meta. That would make sense here, right? And another possible structure that could fit here is we could have our carbon first, and then we could have here, and then we could have our nitrile after it, right? So that would be another structure. So here there's basically 4 structures that really fit this spectrum, all right? And this, we're just learning the basics of IR. It can definitely get more complicated. So there are ways to analyze the spectrum further where you could determine whether this was ortho, meta, or para, or even a mono-substituted benzene ring. But that is not something we need to encounter at the undergraduate level at all. So any of these 4 structures would make sense and be really solid structures for this IR spectrum. All right, let's look at our last problem here. Okay, again, we start with our formula. Let's calculate our dBs or DUs. 2 carbons plus 1 minus the number of hydrogens plus halogens. That's 3 plus 1. That's 4 over 2. All right, so here we have 3 minus 2. We have 1 dBe. So we have 1 pi bond or a ring. So only one of those. Let's analyze our spectrum. As we go through here, I kind of have something that looks like it's starting in zone 1, but man, this giant peak here is clearly into zone 2. So we've got a big peak here. What is that peak? Well, what we should remember is that is our OH of a carboxylic acid, right? When that extends all the way into zone 2, that is a OH of a carboxylic acid. I have a couple of small peaks sticking out between 3000 and 2850. Those are sp3c to H bonds. Here, I clearly have a giant carbonyl peak, a C double bond O. That C double bond O here is the C double bond O of my carboxylic acid. As we get below 1500, we can kind of ignore these. So we're really done with our analysis. One thing I want to point out about this spectrum, I've included this one specifically, this isn't a great spectrum, right? Our peaks are pretty broad. Here it's hard to see. This is some small peaks we have to ignore. So it's not always going to be perfectly clear. On the exams and the questions, I'll try to make them as clear as I can. But in the real world, some of these IR spectrums are not always going to be great, all right? But from here, we can clearly tell we have a carboxylic acid. There's only one possible structure we can have because we only have 2 carbons, right? We've got 2 carbon atoms. So I draw my carboxylic acid. This then has to be connected to my second carbon. So what's the only thing I'm missing? I've got my carbon, right? My 2 O's. What else do I need to add? I have a chlorine that can only come on this carbon here. So there is, in fact, only one structure that fits this IR spectrum, and that is this compound here. All right, so those are 3 examples to kind of just show you how to analyze your IR spectrum and come up with some possible structures that fit.